Oh, hey, it's you guys again. Thanks for joining me. I've got the baseball out again because we're going to look at, a baseball problem again today. We're going to look at this projectile motion. Okay. The other day we looked at this problem. I showed you a clip of a home run being hit where we had a function, it's right up here. We had a quadratic, okay, whose graph is a parabola, and we modeled, the horizontal distance versus the height. That's what this equation did. If we watch that ball travel, the horizontal distance versus the height, that graph, it's pretty easy to see as a parabola. But I mentioned that oftentimes, instead of graphing the horizontal distance versus the height, we graph the time versus the height. And that is actually a parabola as well. It's a quadratic. It's not the same that we see like this, but nonetheless, if we graph time versus height, we get a quadratic as well. So, for some reason my video screen's not showing up. So I hope you can see me. If not, that's all right. So projectile motion. What is projectile motion? Whenever something is launched into the air, released into the air, whether it's dropped, whether it's thrown, whether it's shot, whatever it might be, if the only force acting on the object is gravity, we call that projectile motion. So, if I fly a drone, that's not projectile motion because that has something that is powering it and changing it. There's not the only force acting on it is gravity. So projectile motion would be things like throwing a baseball, shooting an arrow, dropping a water balloon, things like that. I've given you two equations here. One is where the height is measured in feet and the time in seconds, and the other one where the height is measured in meter and the time is in seconds as well. So based on the units that you're working with, whether it's customary or metric, we have to choose the right equation. You'll notice the only thing that's different here is that in our feet equation we have a negative 16 in front, and in our metric, our meter equation, we have a negative 9.8. Why those numbers? It has something to do with the acceleration due to gravity. You may recall that the acceleration due to gravity is 32 feet per second squared, and the acceleration due to gravity in terms of meters is negative, hold on a second. Now I just recalled that I did not type this in. The acceleration due to gravity in meters per second is negative 9.8 meters per second squared, which is why this equation actually shouldn't have a negative 9.8 in it. It should have a negative 4.9. And I kind of give away the relationship between the acceleration due to gravity there and this leading coefficient. The leading coefficient is half the acceleration due to gravity. And you might be asking why, and that's why I'm excited to teach you calculus later, where we can understand where these equations come from. So there's a lot going on here. So h of t, that's the height with respect to time. Notice there's a t, that's a variable in there, that's the time in seconds, but we have a couple other things. We have this v sub 0 and this h sub 0. What do those represent? V sub 0 is the velocity at time 0. That's why we put a little sub-zero here to remind us that's the velocity when time is 0. It's also referred to as the initial velocity. H sub 0, that's the height at time 0. Or the initial height. So if we know the initial velocity and we know the initial height, all we have to do is plug those in and we have this quadratic that models time versus height of a projectile. So, first problem. A water balloon is dropped off a balcony from a height of 100 feet. How long does it take the balloon to hit the ground? So, I have a baseball here, not a water balloon. I'm not going to drop a water balloon right now. If I drop a water balloon or a baseball, there's again two things that we need to know according to that quadratic. We need to know the initial velocity. We need to know the initial height. If I'm just dropping it, what's the velocity? What's the speed of the water balloon when I let go? It's 0, isn't it? Okay. So when we look at a water balloon is dropped off a balcony from a height of 100 feet, we know the initial velocity is 0, and we know the initial height is 100. So let's write an equation for this. H of t, the height at time t, equals, okay, we've got two options for equations, don't we? Which one am I going to use? Well, let me look at my units. Feet. That tells me I'm going to be using this first one. -16 t squared plus, okay, how's it go? V sub 0 t, the initial velocity times t. What did we say that initial velocity is when we're dropping it? We said it's 0. So 0t plus h sub 0, the initial height, that's plus 100. So in other words, the function for our height with respect to time is -16t squared plus 0t, that's gone, plus 100. That's a quadratic that models it. Okay. If I plug in a time, I get a height. So for example, if there is at 1 second, we get what? -16 times 1 squared plus 100, it's at 84 feet. After 1 second, it's at 84 feet. Nice. What am I asking here though? How long does it take the balloon to hit the ground? How do I use this to figure out how long it takes to hit the ground? Well, what do I know when it hits the ground? I know that its height is 0. 0 equals -16 t squared plus 100. Is that an equation that we can solve for t? You bet, absolutely it is. What I want you to do now, okay, two-step process. Okay, I want you to solve this equation for t on your own. I'm not going to do it in this video. I want you to do it. And number two, I want you to check your answer. And think about how could we check our answer here? We want to find where is this equal to 0. We know we can solve that equation for t, but how could I check it? Okay. What I want you to do is I want you to graph this function. Okay, get into Desmos, graph that function, and look for when the height is 0. In other words, what are we looking for? The x-intercepts. So go ahead, pause this video, solve for t, check it by graphing. All right, good job. Welcome back. Okay, good job solving that. Good job checking it by graphing. I hope that worked out well for you. I'm going to look at something a little different now. Okay. Now we're going to actually throw a baseball. Instead of just dropping a water balloon, we're going to launch a baseball. Okay? And we're going to throw it 80 miles per hour. We're going to bring the heat. Okay? And we're going to throw it directly upward. We're going to throw this 80 miles an hour straight up in the air from a height of 6 feet. Okay, so I'm launching it. You know, I'm a little over 6 feet tall. I'm going to launch it from about the top of my head. Okay. What is the maximum height of the baseball, and how long does it take to land on the ground? So notice, if I throw a ball straight up in the air, okay, eventually what's going to happen, gravity is going to overtake it, and it's going to come straight back down. Okay? So the path is still a line, isn't it? Okay? But the graph of time versus height is still a parabola. Let's set it up. Okay, which one am I working with here? What are my units? Because remember, we have a feet equation and we have a meters equation. The units that I have are, okay, 6 feet. So I know I'm going to use my negative 16 equation, negative 16t squared plus the initial velocity times time. Now I have initial velocity because I'm throwing this thing. Okay, I'm not just dropping it. It has, in this case, an upward velocity. Okay, what is that initial upward velocity? 80 miles per hour. Oh, I can't just put in an 80t here, can I? Because what are our units in this equation? They're in feet. And what is time in? Seconds. So we have to do a little extra work. We have to take 80 miles per hour and we need to change it into feet per second. Good. Okay. So let's do a little math here. A little computation. If I change hours into seconds, I know my hours need to cancel, so I'll put 1 hour up there. 1 hour is 3,600 seconds, right? 60 times 60. Those cancel. Now I'm going to change miles into feet. I need miles to cancel. I'm going to put 1 mile down here. I know that's 5,280 feet. Miles cancel. Notice I'm just left with feet in the numerator, seconds in the denominator. I'm going to grab my calculator. There it is. 80 times 5,280 divided by 3,600. I get 117 1/3 feet per second. All right, so back to our equation. What needs to go in here? 117 1/3. I don't really like putting fractions in here. I'm going to round. We're just going to do that here. 117.3 t plus my initial height is 6 feet. There's my equation. All right, now what do we want to find? Max height and how long to hit the ground. Two things. Okay, and again, I'm going to let you take over, but I'm just going to remind you on what we're looking for. Max height. Where do we find the max height of a quadratic? At the vertex. Find the vertex. You know how to do that. Okay. Second thing, how long does it take to hit the ground? Okay. This is like the water balloon question. What do we know? That's when the height equals 0. Can you solve this for when it equals 0? Again, I want you to pause the video. I want you to answer both of those. You know how to do those. Okay. I want you to check your answer with Desmos. Okay. I'm going to sign off. This will be my last example for this lesson. Good luck with today. I love the applications. We get an interesting problem, solving something that's meaningful. So good job. Thanks for tuning in. We'll catch up with you later.